Okay, that works too. Thank you for being here, whether you were forced to or it's for extra credit. I appreciate it. This is the research that I've been working on while I've been here, and is titled, well, it's about being able to determine or detect bacteria using the instrument, the differential scanning calorimeter.
You have to, the wheel on the right side, roll it down to go forward. Is it not working? I haven't used it for years. You might have to, sorry.
Is it plugged into the computer?
Yeah.
Okay, so just a very basic overall understanding of the differential scanning calorimeter. It's a machine that is able to get a lot of information by inputting a heat flow to get a more physical understanding. And so it compares the difference, a major part of it is comparing the difference of enthalpy between a reference sample and a sample. And by doing this, it's able to create thermal measurements. And so inside the machine, which we can see right here, there are two crucibles. The first crucible is the reference crucible. It's normally empty or filled with water. And for all of our purposes, we left it empty. And then there's the sample crucible, which has some kind of liquid or polymer or some kind of sample in it. And so as heat goes into both of them, the amount of heat and the heat that is required to melt or create a phase change is measured. Okay, so the basic analysis that we're able to get out of a differential scanning calorimeter is the phase changes. That's the major part that's measured. So from solid to liquid, liquid to solid. And so whenever we see a positive or an upward peak, that's indicating a melting point at this point right here. And this shows the end of the curve. The area under the curve is the enthalpy required to cause that phase change. And then the downward pointing curves are the freezing curves. So just some data that you're able to get. This is just a little bit of it. You're able to get the change in heat capacity, the delta H, or the change in enthalpy, the melting temperature, the onset temperature, or the freezing point or melting point, and that's just a couple of the data that we're able to get out of it. So the overall purpose of these trials, or my research, imagine walking into a doctor's office. You have a sick stomach, you're feeling nauseous, you have a fever. The doctor is going to automatically say, okay, it's a possibility that they have a bacterial infection, or a bacterial infection. And so to be safe, because doctors don't want to be sued, they give you antibiotics. Sadly, antibiotics are often misused, as well as the fact that they're not always needed, because these symptoms are so widespread with so many other possibilities. And so even though antibiotics are given for the doctor's safety so that they don't get sued, it would be best if the over-distribution of antibiotics could be prevented. And so it was all based on this equation. This is an equation for the change in freezing point that we've all learned in general chemistry, maybe not, hopefully. And so it's the change in freezing point equals the constant of the solution times the molality of the solution. And so our idea was, if we heat the bacteria, if we allow it to grow for a period of time, the concentration, the molality will increase, and so we'll get this constant phase, this constant shift in the curves that will change the freezing temperature, that will allow us to be able to detect the presence of the bacteria. So our project overview was to first find a method that could determine the presence of the bacteria, and to find the different analyses that would be able to detect that. Our scope was initially the bacteria found solely in human blood, However, we used whatever bacteria was available to us at the time. We can click through this one really quick. So our first milestone was to create a method, but we ran into a problem, and the results that we were getting weren't what we expected. And so we also had to understand supercooling. And so supercooling is this effect that happens when you freeze something really fast or really slow. And what happens is it goes below freezing temperature, so water freezes at 0 degrees. However, what we found here was that the water wasn't, when we were rechecking and trying to understand why the results weren't what we expected, we found that as we froze it at different temperature, at different rates of cooling in kelvins per minute, the freezing temperature would not be at 0 degrees Celsius, but instead it was at negative 14 degrees Celsius to negative 20 degrees Celsius. And so we did a series of runs with rate 2, 3, 7, 20. And here on this graph is shown rates 2, 3, 10, and 20, which didn't, because the rate of cooling was so fast, the 20 wasn't able to hit the freezing temperature. But what we saw is that as the rate of cooling increased, the freezing point of the solution decreased or became more negative. And so right off the bat, we were able to see that there was changes in the onset and time variance, and also slight changes in the area under curves. So here, this is showing the graphs for, these are box plots, Box-Musker plots for the freezing curves. And this is comparing rates 2 on the right side and rate 3 on the left side. And so this is showing the area under the curve and the difference between them. So this shows a very clear difference, very significant for the difference in area between rates 2 and 3. And then here, this shows that at least for rate 3, the onset could be expected to be much more negative. However, these values were a little bit more scattered or had a larger standard deviation. But overall, from this, the really important take-home messages are that the onsets are extremely low, being between negative 14 and negative 16, just for rate 2 and 3, and that does decrease more as you get into rate 7 and 10. But also that the rate 3 can be expected to be a lower temperature, freezing point. And so then we decided, okay, now we know that there is supercooling happening because of the rate change. And so this is the equation that we found for it. It's not really that important, but I worked really hard to try to figure it out. So with a lot of help from Dr. Scott and Dr. Cannon, and also some of the teachers in the math department, specifically Dr. Helms. And so we were able to put this equation together that says that as the rate in kelvins per, or the rate of cooling, as the rate increases, as the rate of the change in temperature increases, or heat flow, the freezing temperature increases also. And so that is what we saw, which is important. Okay, so another important part about understanding supercooling was with the melting curves after the supercooling. And so we did a series of runs for this, and after we were able to just get a general baseline, we felt more comfortable moving forward. But there was something else that, you can move forward. So these were also the same graphs, but for melting curves instead. And so we can see that even for melting after supercooling, there was this significant difference in onset and a little bit in area between the curves, between the rates 2 on the right and rate 3 on the left again. And this, it's a possibility, we can't say that it's a for sure thing, but there is a phenomenon that is called dendritic freezing, dendritic capsule freezing, that only happens for supercooling in cylindric capsules where it freezes, the water freezes unevenly, or the solution freezes unevenly, and they freeze in these plate-like structures that then causes the melting to be happen in pockets, and so it happens unevenly. And that is shown in the next graph here. Because of this variance in the incline of the curves right here, as you can see right here and right here, as opposed to the 20 microliter, this is what we thought was happening. You can click again. Oh, maybe one more time. Yeah, one more time. And this could have been happening because the capsule was just too full. 40 microliters might have just been too much, and so this uneven freezing was happening. And so we did decide that because of this uneven, or the variance in the incline of the curve, that the 20 microliters was a lot safer to go with. It was a lot more precise between runs. And so we finally were able to come up with our standard method for freezing and melting. And so for our bacterial samples, what we decided to do was start at a negative 30 degrees with a 15-minute isotherm, and then increase the rate to 37 degrees at 3 kelvins per minute, which was the fastest and most precise. And we also did a 20 microliter sample to prevent that variance in the incline of the curve. Okay, perfect. Okay, so we figured that out. And then we wanted to move on to LB because we needed a baseline for our bacteria. And so we did experiments with our bacteria. These were the graphs that we got. And when analyzed, the best combination, so many different analyses are possible with the differential scanning calorimeter. This is just showing a few of them for each of the curves. A couple of them were chosen and exchanged and done on the x-axis and the y-axis, and the ones that were decided best later on when analyzing the LB samples with the bacterial samples was onset on the x-axis, peak height on the y-axis, and peak temperature as the size of the ball. Okay, perfect. Okay, so something that is good to mention for later slides is that when the peak height is eliminated and only the onset and the peak temperature are analyzed, is that they kind of cluster up together. And so that's an important point that I'll bring back in for the next couple of slides. So we figured out LB, we had our baseline, and then we wanted to move on to bacteria. And so what we found for bacteria, using identical parameters, is we did 2 separate kinds of bacteria, and we would have done more, I would have done more, but I ran out of time. And so I am hoping to do more of this, or hopefully someone will continue this. But we did Pseudomonas aeruginosa and Pseudomonas putida. These were run on the differential scanning calorimeter the exact same way as LB, with the same amount, same parameters and everything. And these were the graphs that we got for those. And the same thing happened. When you eliminated the peak height, they all scrunched up to the same general area, which is another thing that we'll bring in. And so we were able to figure out the bacteria, so now we just had to analyze our results. And this is, again, some of the analysis that we did, just showing how many different things you're able to learn about the curve with the DSC. Okay, so when we put it all together, what we were able to find is that here are the LB measurements. And not only was the differential scanning calorimeter able to say, okay, this sample does have bacteria in it, but it's also able to differentiate between 2 bacteria even within the same family. And so what we expect to see as more trials, or this is run several more times, is that this will turn into some ovular shape here, this will become some ovular shape here, and this will become some ovular shape here. However, when run on a 95% confidence interval, these are still significantly different between the two Pseudomonas, Arganosa and Putida. Yeah. And that's just showing that the bacterial samples are differentiable from the basic broth or from the standard. And so again, what we expect to see in the future as more trials are done are these 3D parameters that we're able to set, where if we do this for a bunch of different bacteria, and a sample is run on this unknown sample, if you don't know if there's bacteria or not in the sample, if it lands in this area, okay, then there's nothing in it. There's no bacteria in it. But if it lands in this area, then there's Pseudomonas aeruginosa. But if it lands in this area, it's Pseudomonas putida. And this is ideally done, the overall idea is to be done for bacteria that could be found in the bloodstream. And so this could be applied to that. So currently, we know that bacteria can be detected using the differential scanning calorimeter based on onset, peak height, and peak temperature. However, we don't know how low the or how high the concentration needs to be in order for the bacteria to be determined, and so that would be something that could be done in the future. But another important point is that we are able to differentiate between bacteria even within the same family using the differential scanning calorimeter. So is it detectable? Yes. Are we able to tell the difference between bacteria? Yes. And what concentration is detectable would be the next step. Okay. And these are just some issues and resolutions. I went through a bunch of different parameters. I'm not sure if maybe I missed some combination of them that could be that could create an even larger difference to make this easier to see. But yeah, so I just wanted to say thank you to these people. I'm grateful for them and their help and support and for tolerating me.
All right, so are there any questions? Any questions about the work here?
Could you go back to, I think, I'm guessing maybe slide 8. Like that first equation you put up there about changing the temperature.
Yeah.
Yeah. So, yeah, the change in your freezing temperature equals the freezing constant
Yes.
multiplied by molality.
Yes.
So you said that you would warm a sample of bacteria, let it grow, plot it, and then be able to calculate or find what that constant is. Is that the idea?
So, if I understand your question correctly, the idea, like if applied to an actual clinic, is that so the idea would be to pull out a milliliter of blood sample from a person who shows these symptoms, and take 20 microliters of it, put it in a sample, and run it on the differential scanning calorimeter to create what was for us our LB samples. It would create a standard, a reference, a background, exactly. While that was running, the rest of the a blood sample would be put in an incubator for 45 minutes, which is about how long it takes to run each of these samples. We put in the incubator for 45 minutes to allow it time to incubate and replicate. And then that sample would be run again on the differential scanning calorimeter, creating a shift in, if you could go back to the last graph.
Very nice one.
Yeah, with the 3 samples. So if our background was right here, or the blood, including the red blood cells, white blood cells, all of that stuff, was right here, or it could be over here, or wherever it would be, we would expect to see a shift towards the direction of the bacteria as the concentration of bacteria increase. And so if necessary, if instead of moving all the way down here, it moved right here, worst case scenario, you run it again and it moves further down.
I guess I'm a little confused because, so you're gonna heat this up to grow the bacteria? It seemed like the whole presentation was about cooling it, right? Freezing temperatures?
So the freezing part of it was mostly to understand the supercooling effects in the beginning, but also it does need to be, because the differential scanning calorimeter measures phase changes, it does need to be frozen before it can, so that it can melt and so that we can get the information from the melting curve.
So you heat it up to grow the bacteria, then you put it into the DSC and freeze it.
So they're two separate samples. So the first one that we run is without incubation. So we just pull it right out of the blood and run that sample as the background. But the other sample, yes, you're
Okay.
correct. We
Okay.
incubate it and then run it.
I have another question.
Go ahead.
I keep going. My other question is about supercooling. So I think what I understood from supercooling is that the faster you cool it down, the colder it gets.
The faster you, the faster, so the higher the rate of cooling, the faster you cool
The
it.
faster you cool it down, the faster it gets cold.
The more negative the freezing
See, I
point.
understand this, but that's different than what you just said. I thought you were saying the faster you cool it down, the lower the freezing point is, like the actual colder it is. Not just it's getting colder faster, but it's actually getting colder.
More supercool.
Is that what that means? Okay. So then, does this mean that it does not have a freezing point? It has a freezing range, depending on how fast you cool it?
It does have a freezing point. However, this freezing point does change based on the rate that you're cooling it at, which was one of the reasons that I spent so much time trying to find this equation, is to be able to explain that it does have a freezing point, but because of the rate change, the freezing point is changing. And so yeah.
Might part of the reason for your supercooling be, your crucibles are sealed, right?
Right, so constant pressure.
Now, are they, does it allow gas to escape? It's sealed,
Closed
so
system.
It shouldn't.
shouldn't.
Yeah, it should.
The larger your sample, so what you're saying, you're filling up the entire crucible with that 40 microliters, and it's trying to freeze, it's trying to expand, you're putting it under pressure, and so you can lower freezing temperature by changing the pressure. So it's not just supercooling, you're also pressurizing it too. So when you changed it to 20 microliters, you didn't see as much supercooling. Is that right?
There was the same amount of super.
Same amount, the smallest sample. You said you went to a smaller sample for a reason though, right?
Yes, and that actually that could be one of the reasons for the variance in the curve that's actually one of the other reasons that we changed to a 20 microliter sample is because the 40 microliter sample filled the crucible up about as large, the meniscus
Yeah.
was pushed down by the cap when it was.
And that would prevent it from freezing because it can't expand.
Exactly. So or the expansion could have even created pockets or holes in the cap. And I don't know how strong that pressure would have been, but that's another reason why we just avoided the 40 microliter samples.
Another
We just
related
don't-
question. You said you ran your reference cell empty?
Yes.
Why didn't you put solvent in there?
That was just our initial decision to run our reference as empty, just to take away any possible background from the machine itself, just in case there were any problems with the machine.
But then you see, think about that. But your samples, your cell samples are just a cell solution in LB, right? You're writing it in LB. So why would you want to put the LB in the reference cell? That's just so you just see the effect of the cells. Compared
That
to
is
the
something that we
LB
haven't
alone.
done yet, but it is something that we could do in the future.
Well, it would be ideal, but with all these little supercooling quirks, if the peaks get off slightly, then all of a sudden it's just a mess, right? Because it's gonna go up and down. You're not going to have that. It'd be nice if here's one peak and here's the other peak and they're almost exactly the same, and then you just subtract one from the other, you see that little bit. But there's enough variability that if it gets off slightly, then the peaks no longer look the same, and your trend of what you're trying to monitor depends too much on that how the machine's feeling that day. So.
I have a question. Sorry, I'm not a professor, so this is going to be a dumb question. But and if this is beyond the scope of what your guys' project is, that's fine. But just thinking about your application where you said you're going to pull the blood out and let some of the blood incubate, and then have your standard be your blood that you freeze immediately. How are you guys sure that the immune response still contained inside that blood, whatever white blood cells or antibodies you may have, will not inhibit the growth of your bacteria and then give you a, what would that be, a false negative? Because you wouldn't have any growth difference over 45 minutes. Have you guys considered a filtration method for that or something along those lines? Because we don't have LB broth running through our veins.
I have not thought about that. Dr. Scott, do you have any?
that might be beyond the scope of the project, and that's fine. But I'm just thinking like the process
That's a
would.
good question.
If your blood can prevent the bacteria from growing, then it's doing its job, and you don't want to start taking antibiotics, I guess. But if the bacteria there is going to grow, continue to grow in the blood, then if you all of a sudden dilute the blood with something that it loves more, which would be LB broth, then it should grow.
Oh, so you guys are going to dilute the blood with the LB
Just
broth?
a tiny little bit of blood would be
Oh,
put
okay.
into
I thought it was going to be. Okay, that makes more sense. Okay.
Any further questions?
All right, let's thank Leanna.